Today for our Closing the Loop webinar. We have Jason and Jordan here ready to share with all of you. There will be time at the end for questions, and I'll ask that you put those in the chat, and we will answer those at the end of the event. So, Jason, I'll let you take it away.
Yeah, sounds good. Thanks, Jessica. Thank you, everyone, for joining. I do see a few familiar names on here, so thanks for showing up again. For those that we have not met yet, also thanks for joining. But just by way of background, so I'm Jason Bowman. I oversee our industrial wastewater and biogas division for the North American market. Have been in the industry for roughly 18 years, 17, 18 years, and have had a strong focus on industrial wastewater during that time. Jordan Privet is with me. Jordan, would you like to give a quick intro?
Yeah, sure. Thanks, Jason. I'm Jordan Previtt. I am the national sales manager for our industrial water and reuse group here in North America, and I've been in the water industry for a little over 10 years now with a couple different OEMs, and happy to start this webinar and give you guys some good information here.
All right, sounds good. Well, thanks again, everyone. So we will walk through Closing the Loop, a complete guide to the industrial wastewater or water cycle from source to reuse.
Okay, so we should be able to wrap this up within 45 minutes, but here's what we would like to cover today. For starters, for those of you that do not know Fluence, we'll give a brief 2 to 3 minute introduction on our company background, and then we'll move into what exactly the water footprint and water cycle means for industrial operations. Jordan will provide an overview of the general water treatment practices and the technologies we offer to help solve water needs. After that, I will provide an overview of our wastewater solutions and how wastewater treatment strategies tie directly into maximizing the water cycle and minimizing waste before discussing applications about wastewater reuse. Following that, we will end with a brief Q&A. So I hope everyone is able to learn something from today's presentation. So let's get started. For those of you who are not aware of Fluence or perhaps have worked with one division but not other divisions, just as a quick background, we focus on the complete water cycle. So this means everything from municipal and industrial water, as well as municipal and industrial wastewater, all the way to a dedicated reuse and desalination divisions. So beyond those 6 key divisions that I mentioned, we are a multinational company. So we have operations in roughly 10 countries. That includes manufacturing, back office engineering, sales, management, etc. But we cover closer to 80 countries in terms of projects execution and project support. Specific to today's topic, our centers of excellence for industrial water and wastewater have historically been situated in Europe and South America, but within recent years, we have expanded our North American operations to support these divisions specifically. For the purposes of today, if we look within our industrial water group specifically, our main focal areas are within the food and beverage space, the food and beverage industry, as well as energy and power generation, general manufacturing, mining, and desalination or brackish water treatment. If we turn our attention to the industrial wastewater group specifically, our main focal areas fall within the food and beverage industry as well, with meat and dairy being a significant portion of our experience. But beyond that, meat and dairy and the general food and beverage industry are where we focus. But we also have experience in production of alcohols, pulp and paper facilities, as well as pharmaceuticals. And just as a quick note before we get into the water cycle and the water footprint, it's important to note our project approach. We are a solutions-focused organization, so this means we typically provide the balance of the engineering for most facilities. This usually includes engineering like architectural engineering, mechanical engineering, electrical, plumbing, process engineering, etc. So we generally take ownership of the engineering element through the full-scale commissioning and startup of these facilities. So enough about Fluence. We are here today to review the industrial water cycle. So let's talk about why the industrial water footprint is so critical. Why is it then important to understand our or the industrial water cycle and water footprint? Well, for one, it really helps to put water usage into perspective relative to our own daily use, but also from industry to industry. Not all products are created equally, and right, wrong, or otherwise, some products require significantly more water than other products. So, what are our main goals for today when discussing the water footprint? Well, making us aware of how we're using resources can help reduce the need for freshwater intake at these industries. It can also help us plan ahead for future years and plan expansions by identifying and combating potential current or future water shortages ahead of the game. But more importantly, it allows factories and industries to take control of the situation and provide their own internal independence. I've always found this table to be interesting. It lets us look at the water footprint for several of our common everyday goods. So if we look at the little blue drops, those are blue drops of water, and each one represents 50 liters or 13 gallons that is required to produce this product. So again, we're not here to point fingers at one industry or another, but it is clear in just about every case that water consumption is a major part of the production process. Now, in our everyday lives, I doubt that many people or consumers on an individual level think about consumer goods this way, but I can almost guarantee you that the factories producing these goods understand exactly how much water is being used. Beyond understanding the consumption rate for a given product, we also need to understand where and how much of the resource, that is the water resource a given area can provide. As our population density and manufacturing density increases, so does the water usage or water uptake rate. And this graph is really nice. This is provided by the United Nations. It may be a bit outdated, but it highlights areas of mild to extreme water stress across the world. This basically maps out how much fresh water is being withdrawn in a given economic region, or more specifically, it is the relationship between total water used and total water available. As much as we'd like to think that we have an abundance of fresh water, it's quite clear that most developed regions of the world are already overexploited. And this certainly creates a perspective that we will more than likely run into issues in the future if we do not change the current consumption rates. Then the US specifically, we see regions of heavy withdrawal depicted here in the darker blue regions. So this is what's called the self-supplied withdrawal map, meaning surface water or aquifer or groundwater being used as the intake source. So there are several regions on this map here within the US that alone are withdrawing billions on a daily basis. That's such a staggering number. Now, again, this is a little outdated, but you could clearly piece together where the densest manufacturing regions are in the US. So all that said, sorry if I scared anyone, but it's important to really put these things into perspective if we're going to change the way we approach water. Moving on to the water cycle, let's look at how industries use water before we move into common practices of treating or managing resources internally at these factories. Here we have just a simple sketch of a typical factory, and I am using air quotes when I say the word typical. All industries are going to receive water in really one of 5 ways. Number 1, from a public works, 2, from groundwater, 3, from surface water, 4, potentially from ocean water, depending on where you are in the world, and number 5 If you're already ahead of the curve, you may have a closed loop recycle or reuse plant at your facility already. In all cases, some form of treatment will be required to ensure the water quality meets the site-specific demands. So this could be specific dissolved solids content or ionic contents, conductivity, turbidity, etc. Generally, after the intake water is used in really one of 4 or 5 main ways, and these are cooling and heating, cleaning and sanitation, and sanitary. In other cases, at specific sites that may require energy generation or a reactant for a specific solution, or even ingredients in our favorite food and beverages. So this is all pretty basic stuff. Let's talk about the principles and technologies behind these operations that help us ensure that we are meeting specific standards, that we are maximizing our water potential, and that we're ensuring that we're keeping a sustainable and or optimized facility. For that, I will now turn it over to Jordan, and I will be back to talk about wastewater after Jordan has finished.
All right, thanks, Jason. Yeah, so as we initially mentioned, the next handful of slides that I have will detail some of the most commonly used treatment technologies in the industrial setting to treat water for a multitude of downstream applications. These are by no means the only available options for treatment, but are the most prevalent across many industrial applications. Before we jump into some of the specifics on these technologies, I think it would be useful to first understand some of the most common applications that the resulting treated water will be used for. These applications will obviously differ based on the exact industry focus, but common uses range from boiler feed water to steam generation to process waters, cooling tower makeup, heavy metal removal, resource recovery, desalination, and the list goes on. Commonly, these systems and processes will be utilized for solids reduction, hardness removal, iron and manganese removal, dissolved solids removal, and treatment of concentrated brine for resource recovery. As it relates to Fluence's direct capabilities in this space, we typically focus on providing integrated system design that we can treat the varying incoming feed waters to the customer's site-specific needs. This usually involves using media-based pretreatment options, membrane-based UF and RO, EDI and CDI, and ion exchange, ozone and UV to purify the feed water. As we start to look into the potential reuse applications in the industrial world, a lot of these same type of technologies will be applied to these streams as well. But proper pretreatment to the reuse waters will need to be carefully considered and is important to ensure successful implementations. Additionally, Fluence's design package focuses on pre-engineered system footprints that allow us to shorten the time frame between design and installation and startup. And our integrated design systems typically provide an automated skid-mounted unit that can be installed in existing site infrastructure or containerized for implementation in almost any circumstance. The setup also allows for seamless capacity expansion with plug-and-play unit capabilities. Many of these applications that we as Fluence work on in the industrial sector are deemed high purity applications. So one more note that I think is useful for this presentation is that it just quickly puts some parameters on what high purity water actually looks like for many of our customers. Now it can differ from industry to industry, but generally we can look at water quality based on the final dissolved solids content. Now, typically in a municipal setting, water TDS, they're looking for something at or below 1,000 milligram per liter, while general manufacturing and power facilities require much tighter treatment with resulting TDS at or below 100 milligram per liter or 10 milligram per liter respectively. And then industries like the semiconductor industry generally have the tightest treatment requirements and usually look for TDS at or below 1 nanogram per liter, which can also be referred to as ultra pure water. Ultimately, the level of water purity that is required in the plant process will determine the final treatment processes. Okay, so now we'll get into some of the specifics on equipment used to treat the incoming feed waters for the aforementioned industrial applications. The next few slides will be a general overview of these treatment technologies and aren't necessarily supposed to be an in-depth review, but we can certainly set aside some time outside of this webinar if this is of interest to anyone here. Now, as we start to look at the potential feed water sources at your site, you may find that a prefiltration process is necessary. And in today's day and age, one of the most commonly used technologies for this will be ultrafiltration or microfiltration. And these are also commonly referred to as UF and MF. For the purpose of this webinar, we won't really get into the differences between UF and MF as they're generally fairly similar and can, in some instances, be used interchangeably. So ultrafiltration is a great first step in your treatment process and is most frequently used for the removal of suspended material from your feed water. In addition, these membrane systems can also provide a level of pathogen removal. There won't really be any sort of removal of dissolved contaminants at this stage in the process, but as you'll see in the next stage, that'll be handled for a majority of that contamination. As these systems are such great pre-filtration stages, they're commonly found in municipal drinking water facilities, as well as they're the initial step in a higher purity application. I will also note that UF and MF aren't always the only pre-filtration systems that can be applied for suspended solid removal. Media filtration is also an adequate treatment option and at times can be paired with UF and MF for enhanced solids removal in particularly tough waters. All right, as we move further down the line of the treatment processes, another commonly used technology will be nanofiltration or NF. While it's not necessarily the most prevalent in the industrial world, it does have its place in a potential treatment scheme. These systems essentially operate in the same equipment platform as the reverse osmosis systems, with just some key operational changes such as the feed water pressure that's necessary to operate these systems. The main advantage of an NF technology is its ability to remove only divalent ions from a water source. Most monovalent ions will remain in the resulting permeate water from this process. NF is a great option when ultra pure water isn't necessarily required and or if color might need to be removed from the water source. Oftentimes, this technology is utilized in municipal drinking water facilities as a softening stage before being sent out to distribution. There are also applications in the mining industry that NF can be used as a sort of pre-filtration stage ahead of an RO in a brine treatment process. As we move down the spectrum on the available treatment processes, we next have reverse osmosis or RO. This technology tends to be the most frequently used in a higher purity application and is oftentimes referred to as a workhorse of the operation. Similar to NF, RO is a spiral wound membrane that will remove a large majority of the dissolved contaminants from the feed water. The technology is very effective at removing both monovalent and divalent ions from the water and can generally remove upwards of 99% of the dissolved contaminants that are present in the feed water. It can be susceptible to fouling and scaling, so you definitely want to make sure that you have proper pre-treatment in place. Oftentimes, multiple RO units can also be run in series to either increase recovery or maximize the dissolved contaminant removal. This is commonly referred to as RO stages or passes. A multi-stage RO will yield the highest recovery of the feed water, while multi-pass units will yield the best TDS removal, ultimately providing a higher quality finished water. The multi-pass permeate water is optimal for further polishing utilizing ion exchange technology, which we'll talk about here in the next slides. Another key item to understand about RO treatment is that there are limiting factors in the number of passes and or stages that can be implemented. At a certain point, dissolved contaminant removal will be minimal, and the energy required for pumping the highly concentrated water will outweigh the minuscule contaminant removal that you'll get from it. Additionally, scaling and fouling potential could be a much greater risk to if you put too many stages or passes on a system. So typically, the sweet spot that we like to look for a treatment process would likely be around 2 stages or 2 passes. Right. So in the event that your plant process requires a higher degree of treatment than an RO can provide, the next stage in the process will likely be some sort of ion exchange technology. And while this technology isn't necessarily new to the industry, CEDI or EDI is something that is more readily being implemented at a lot of industrial customer sites. EDI refers to electrodeionization, which is a process that utilizes traditional ion exchange resins, both anion and cation. But instead of being in a pressure vessel, it's contained in a cartridge or a module that allows electricity to be introduced to aid in the ion removal process. Additionally, the technology also allows for regeneration of the onboard resin in situ without the need for potentially dangerous chemicals to be on site. EDI or CEDI, both terms that can be used interchangeably and essentially function the same, provides the polishing step in a treatment process that removes upwards of 99% of the remaining dissolved contaminants in the RO feed water. Typically, the technology will produce finished water quality with TDS in the microgram per liter or ppb range, which would be sufficient for high purity applications. These modules can be susceptible to scaling, so proper RO pretreatment upstream will be required. Optimally, these will be fed with water that has single digit TDS levels. So more than likely a 2-pass RO would be optimal for upstream treatment of these systems. Okay, so the final technology that I'll discuss today is a resin-based ion exchange system. In practice, these provide the same dissolved contaminant removal as EDI or CEDI, but with a resin-based ion exchange system, you can sometimes achieve much higher contaminant removal. As the typical operation is to utilize an anion and cation in separate pressure vessels, followed by a final mixed bed polishing unit. The resulting water will oftentimes be suitable for your ultra pure type applications that would be necessary for your semiconductor industry. Again, this technology will remove upwards of 99% of the remaining dissolved contaminants from the water and typically produce water with TDS levels in the range of nanogram per liter or parts per trillion range. Like I said, we can run multiple vessels in series to produce the highest water quality possible for your ultra pure needs. One of the biggest downsides of a resin-based ion exchange technology is that they do require potentially hazardous chemicals to be on site for the regeneration processes. And in some instances, a separate system might be required to remove the resin from the treatment vessels and move that into a separate area where the regeneration process would be conducted. So, these systems can require a lot more labor to operate and maintain, which is why some of the industries are starting to move away from it. One potential solution could be to utilize EDI or CEDI technology as a polishing stage just downstream of the RO. And then you can also utilize a mixed bed system to produce your final polished ultra pure water. Oftentimes, there are also third-party companies that can provide offsite regenerable mixed bed systems, which would also remove the need for hazardous chemicals to be on site as well. So finally, and I won't go through each one of these individually, but I did want to provide a reference for some of the industries that we typically work in and the treatment processes that are often used. As you can see, a lot of the most crucial processes for these individual operations within an entire plant process utilize most, if not all, of the treatment technologies that we just discussed. And with that, I'll turn it back over to Jason to talk through some of the wastewater treatment processes and technologies.
All right, great. Thank you, Jordan. Let's now turn our attention to the wastewater side of the operation. Going back to our typical flow chart from a typical industry, and again, I'm using air quotes when I say typical here because every industry is a little different. The main contributors to wastewater are generally from the cleaning and sanitation side. Then you have the sanitary systems and potentially from the production process itself. Now, wastewater treatment can consist of many steps, different types of technologies, different types of processes. In most cases, factories will have a minimum of pre-treatment. That is before they can put any wastewater down the drain. This is typically storage like equalization, screening, solids removal, chemical adjustment, etc., depending on the application. In some cases, it can be as advanced as precipitation as the initial pretreatment step. What generally follows these steps will be some form of biological treatment and then liquid solid separation. As the potential for wastewater reuse comes into the equation, then we start to think about how all of these prior treatment steps might impact our ability to reuse water at the end of the process. So that could be the organics remaining in the wastewater, the nutrients remaining in the wastewater, the solids, etc. In almost all reuse cases, having a stable and reliable secondary wastewater treatment plant is critical, as this usually ensures the removal of contaminants that may otherwise impact the efficiency or efficacy of reusing treated wastewater effluent. At this point in the factory, and this point in the process, Jordan's division and my division are relatively separated. Jordan at this point is on the front end of the project, and I typically work on the back end of the project. However, there is a point at which the two divisions kind of cross paths again, and we'll get there momentarily. On the industrial wastewater side specifically, my core focus and our division's core focus is in primary treatment and biological treatment of high-strength wastewater. We also have a wealth of experience in waste to energy facilities, but this is something we'll not cover today. But for the core wastewater technologies, these typically include clarification, dissolved air flotation systems, biological nutrient removal, using conventional methods and more advanced methods. We have intensification processes such as MBR and MABR, and we do have the ability to integrate all of these solutions into one front to back wastewater treatment concept. For most facilities and most situations, before we can think about wastewater reuse, several processes are required. First, from factory discharge, wastewater treatment generally proceeds in the following manner. Initially, we have collection and screening, followed by equalization or chemical adjustment. Sometimes there's a need for metals or solids removal, maybe FOG, and then this is typically followed by biological nutrient removal and the first phase of liquid solid separation. Generally speaking, systems can be designed to meet strict surface water discharge through the first liquid solid separation step, but as we consider going into irrigation or non-potable reuse, additional liquid solid separation processes are required. Still, to produce non-contact potable reuse, even a third liquid solid separation step is typically required. So let's talk about the various technologies that can help complete this water cycle and how we can arrive at a wastewater reuse process. So at this point, we have almost come full circle. Jordan has basically helped balance the front end of the facility at this point, and our industrial wastewater group has provided a first-class wastewater treatment system. So going back to the original goals of this presentation, we haven't quite maximized the water potential yet. From here, from the end of the wastewater treatment plant, we've essentially removed the necessary organics, nutrients, solids, etc., to a point that now we have an option of evaluating whether irrigation or non-potable or indirect potable or even direct potable reuse could be a possibility, and even considering the option of treated effluent going back into the actual product in the manufacturing facility itself. Starting with irrigation and non-potable reuse, the quality requirements of the water or wastewater will and does vary by location. So this can be state by state or even source by source. It also depends on whether wastewater irrigation is considered unrestricted, that is a constant nonstop year-round irrigation, or it may be restricted, which may be a seasonal or time-based variant or agronomic load-based variant, i.e. the pounds of nutrient that you can add per acre per year. In most situations, we will be required to sufficiently reduce the pathogens, metals, total dissolved solids, organics, and nutrients to some high level. So how do we ensure this? Well, in most cases, we utilize tertiary filtration and disinfection, and this is generally a ultrafiltration unit and UV. These can either be a standalone system or can be built into a prepackaged containerized unit. And these units provide the option of reusing water for crops, for lawns, golf courses, cooling towers, boiler makeup in some cases, depending on the exact water quality, sanitation water, and dust control in many areas. Moving beyond irrigation and non-potable reuse gets interesting. There are essentially four directions that most factories will consider. So these are non-potable recharge, indirect potable reuse, direct potable reuse, and product reuse. And in each situation, if we look at this table and as we move from the left side of the table to the right side of the table, the level of pollutant removal increases significantly. Where we initially started with basic pathogen and solids reduction, we now have dissolved solids that we have to think about. We have conductivity, we have disinfection byproducts. And as we move into the more extreme cases like that of potable and product makeup, there's a consideration for micropollutants and even purification. So while these may sound challenging, this is performed every day, day in, day out, in hundreds, if not thousands of facilities. Now, we as Fluence are directly involved and engaged in making these reuse applications possible. So these projects can be need-based, meaning access to sufficient water is limited, or sustainability-based, that is, a factory may be concerned with its environmental impact or even its operating costs. If we go back to the water treatment practice slides that Jordan presented on, so the technologies that we employ to make wastewater reuse a possibility are really the same as that of our industrial water division. So this is where I mentioned that our industrial water and industrial wastewater divisions cross over. Many of the same technologies required for factory intake or process water makeup are the same technologies that are required to make wastewater reuse a possibility. So these may range from your basic microfiltration all the way up to multi-step reverse osmosis, all the way to deionization, ion exchange, and even advanced disinfection. At the end of the day, every project is different. The water chemistry and site restrictions or site goals are what drive the equipment and the processes that will be required to make sure we meet these goals.
All right, so now that we've gone through the technical portion of the webinar, we now have a few case studies that we wanted to share. These will demonstrate real-life applications and designs that Fluence has implemented at industrial customer sites across the world. Um, these will encompass the front-end water treatment of source water, treatment of the resulting plant wastewater, and some reuse applications. The first case study that I have today is for a Coca-Cola plant that required treatment to meet some strict standards for their beverage manufacturing process. The particular water source that we used here had some issues with boron and conductivity levels in the feed water. And as I'm sure you know, the beverage or food and beverage industry has pretty high standards for their processed water. So this required us to come up with a solution to meet these stricter standards. So the resulting treatment system was a multi-stage process that featured a specialty ion exchange resin process that targeted boron for removal. Once the boron was removed, water was then treated with UF for particulate and pathogen removal, followed by RO, GAC, and UV. The resulting purified water was then used in the beverage manufacturing process. And in total, the system was designed to produce just shy of a half an MGD of treated water each day. Additionally, they also required treatment of the ion exchange regeneration waste, so that it could be safely disposed of. For this purpose, we provided a waste neutralization system as well. And this plant was commissioned and installed in 2019, is still in operation today. The second case study that I have here is on a system that was installed at a biomass power plant. These types of plants don't typically utilize an overwhelming amount of treated water, but as you can see, they still need a decent amount of production for their operations. So the challenge at this particular site was that they were utilizing two different wells with differing water qualities as the source for their plant processes. And additionally, the two plant processes required differing finished water qualities. The resulting solution that we came up with for the site was to provide a number of skid-mounted systems to meet their needs. The systems included UF for their pretreatment of the well waters as the initial step, followed by a first pass RO to remove dissolved solids. Majority of the first pass RO permeate was then sent to the cooling towers, as you can see, but then a small stream was reserved for some further treatment. That further treatment consisted of a second pass RO skid that we provided so that it would be suitable for the final EDI polishing step. And this system was installed again in 2019 and has been in operation for a number of years now. It's still running to this day and continues to meet the plant demand for their treated water. The final case study that I have today is on a combined cycle power plant. This plant happened to be located in a geography where the feed to the plant was somewhat limited for their overall requirements. So this kind of understandably created some difficulties in the initial design phases, but ultimately it was decided that we would supplement the well water feeding the plant with some recycled cooling tower blowdown. The resulting process that was designed consisted of a two-part solution. We provided a treatment system consisting of UF pretreatment that allowed for us to reuse the cooling tower blowdown to supplement the well water. And then that treated blowdown was then blended with the well water, which was treated with media filters followed by RO to aid in the removal of high chloride levels. And then a majority of that permeate was used for cooling purposes in the plant. And a smaller side stream was then taken from that water for further treatment with a second pass RO and EDI so to be suitable for boiler makeup. This plant was commissioned in 2020. It's still in operation today. And one kind of interesting and unique thing to point out about this particular design was that due to some spatial limitations, the RO systems were designed with or to be stacked on top of each other. And this just kind of gives you an idea of some of the customization that Fluence can engineer into our designs to meet whatever site-specific requirements any customer might have. And with that, I'll hand it back over to Jason for a few more case studies.
Okay, so moving on to the wastewater reuse side. This case study here is based on wastewater reuse. And the client here was JBS. For those of you who may or may not know JBS, JBS is a large meat and protein processor, a global processor. So in 2022, Fluence partnered with JBS's headquarters to address issues associated with the local municipal water supply, or really the lack thereof, when facing a facility expansion, a processing facility expansion. So to, let's say, combat the impact to the local municipal water infrastructure, again, really lack thereof, Fluence and JBS partnered to develop a reuse strategy, which basically resulted in the construction of a brand new water reuse plant at the factory. The wastewater portion initially consisted of your, conventional primary treatment, biological treatment, with those byproducts and biological sludges and DAF sludges going to a digester system. But then the biological system was followed by a microfiltration process using a chemically resistant membrane, a PVDF membrane, and then followed by UV disinfection to provide high quality effluent. So in the end, the process has a reuse capacity of nearly 1 million gallons a day, which really helps to offload the stress of the local municipal water supply. Okay, so the second and final wastewater reuse case study we have here is a really interesting fish processing application. So this process is quite intensive. So at this facility, the facility is called Tudell. They use evaporation to dry and recover oils and proteins from fish. Essentially, the only wastewater that is generated from this facility comes from the condensate through the evaporation process. Once the condensate is collected, it goes through a cooling tower system before going to the wastewater process. And as you can probably imagine, coming from fish processing, the organic nitrogen and phosphorus concentrations with this specific condensate were quite high. We had COD values reaching 8,000 milligram per liter, and total nitrogen values reaching 300 milligram per liter. So our industrial wastewater group developed a split feed denitrification nitrification process using a membrane biological reactor. So the purpose of the split feed design here was to minimize the internal nitrate recycle rates. So given the high nitrogen value and the nitrate generated through the aerobic process, a normal MLE process would have required an excessively high internal nitrate recycle, which also equates to high energy consumption. So the step feed process helps to reduce the actual nitrate recycle compared to the incoming flow, or the ratio thereof. So the utilization of the MBR process helped to reduce the process volumes as much as possible, while still squeezing in the necessary aeration for such a high COD and nitrogen environment, but also provided high enough quality effluent that could go direct to an RO feed. So in the end, the final RO discharge is fed back to the existing boilers in place of the local fresh water. And the local freshwater here, the access was quite difficult. Number one, they had to truck water from fairly far away. It cost them anywhere from $3 to $4 per cubic meter of fresh water. And then the freshwater source actually had a very high salinity. So prior to the RO system being installed, they constantly had to take the boilers down. So by reusing the RO and the wastewater from this process, they were able to eliminate the salinity issues, the salinity concerns, and really boost their boiler performance. So with that, that concludes our presentation. If there's any questions out there, Jessica, if you have access to, we'd be happy to answer those.
Yeah. Yeah, I have a few on here already. Somebody's asking for the water processing, are you using, what does that say? Water nucleation catalyst to increase reactivity of chemical process, reduce scaling and fouling?
I mean, I guess the short answer to that is I'm not aware of anything that we have done specifically with the NAC technology. And a full disclosure, I'm a little bit newer to Fluence, so I don't have a full idea of all of our applications that we've installed equipment on, but I know that it has been used and it is something that we can engineer into a system process if that is something that the customer would be interested in.
Okay, would it be possible to treat biogas plant sludge wastewater for a zero discharge plant?
Anything's possible, right? I mean, we deal with digestate treatment all the time. I have yet to see like a 100% ZLD digestate process, at least in the US market. Overseas, it does exist. It just becomes a matter of economics, right? When you get into biogas facilities, in a lot of situations, there's tax incentives, there's tax kickbacks, there's credits. But then the ZLD side as well. Again, different parts of the world, Canada, US, Europe, differ in carbon, how they view carbon offset and credits for things like that. So in some situations, going with minimal liquid discharge or zero liquid discharge can trigger kind of a monetary element in some situations. So at the end of the day, from my experience, it's all based on return on investment. If you can't find something within the 2 to 4 year window in a lot of these cases, industrial end users just don't find it attractive.
Okay, are you recovering the excess of acid or base from the IX regeneration process, or are you neutralizing in practical terms?
Yeah, and I'm assuming you're kind of referring to that one case study where we had the neutralization system. And the short answer to that is, I mean, we'll try to recover, as much of the regenerate chemical as possible, where it makes sense, and then neutralizing only when necessary, because obviously that means we're going to be bringing, or the customer would be bringing additional chemical on site. So the goal will be to reuse as much as possible and then only neutralize and discharge when absolutely necessary.
Jason, we have one for you. In your case of JBS, water comes from a slaughter process, and another one, nutrient recovery. How is your technology compared to others?
Yeah, so the slaughter process, yes, it is a fish kill operation. It is kind of a wild situation where they pull from dozens and dozens of local, fish farms, if you will. So, Jessica, do me a favor and read back the second part of that question.
He said, nutrient recovery. How is your technology compared to others?
Yep. So there are a number of different ways that nutrient recovery enters the equation in industrial wastewater treatment. If there's a nitrogen side of things, there's a phosphorus side of things. So in a lot of situations, when you get into slaughter facilities and even dairy facilities specifically, there are magnesium, there's ammonia, and there's phosphates. So we do have a struvite recovery process that we use in these situations to proactively and upfront try to drop out as much magnesium ammonium phosphate as possible. In some situations, we'll add magnesium oxide, so we kind of let's say force the application a little bit if we need to. If magnesium is the rate limiting factor, we can still take out nitrogen as ammonia and phosphorus from the equation. On the back end of these facilities, sometimes there have been designs where we would design a system to fully nitrify, but not denitrify. Now, in most situations, I don't really recommend it, but there is the option of running a high nitrate effluent that's more or less void of organics or ammonia through an RO process. And RO actually has a really high recovery or rejection rate of nitrate, so you can end up with a very high liquid nitrate at the end of the process. That's kind of a growing market. I'd say relatively new within the past year or two. So it's you're not going to find many applications there yet, but on the struvite side, absolutely. In fact, most digester facilities we have side stream struvite removal. Sometimes we do it directly inline in the wastewater plant itself. So it really just depends on the type of process. Anything else?
Looks like I have one more. It says, are you having any case? Oh, maybe in nutrient recovery. Are you having any case studies in nutrient recovery from industrial processes? Jose, is that what you meant? Hopefully you meant nutrient recovery. It just says N, so.
Yeah, okay. In Europe, yes, it's a bit more common. The US market has not quite caught up. So we do have facilities in Europe that do have nutrient recovery, struvite specifically, again, that they can blend or land apply. All right, you guys are going pretty easy on us.
That's all I'm seeing.
Okay, all good.
Great. Well, thank you everyone for coming, for joining us. And I will send this presentation out as soon as we have it downloaded.
Sounds good. Thanks, Jessica.
Yeah.
Thanks, everyone.
Thanks, everyone.
All right.